Okay, good evening. Welcome to the public lecture this evening. This is the third in a series of public lectures organized by the Institute for Mathematical Sciences. My name is Chong Chi Tat. I'm the director of the Institute for Mathematical Sciences. This evening we are very happy to present to you a talk by Professor Renner from the Swiss Federal Institute of Technology. That's Eigenes Technische Hochschule. So that's Federal Institute of Technology, ETH for short, in Zurich, Switzerland. Professor Renner graduated from ETH, the PhD that is, in the Department of Computer Science, where he wrote a brilliant thesis, receiving the ETH medal together with a Best Dissertation Award given by the German chapter of the Association for Computing Machinery, ACM. That was in the year 2005. And then between 2005 and 2007, he was a Hewlett-Packard Research Fellow at the University of Cambridge. He spent those 2 years working with Professor Arthur Eckert in the Department of Applied Mathematics and Theoretical Physics. And 2 years later, he returned to ETH as professor and is now the director of the Institute for Theoretical Physics. Professor Renner's thesis was in the area of quantum cryptography, and his area of research is in quantum information science, as well as quantum theory and thermodynamics. Tonight he'll give us a talk entitled Gambling Against the Second Law of Thermodynamics. Please welcome Professor Renner.
Thank you for the very nice introduction. And I would also like to thank the organizers of the workshop I'm participating for the very nice time here. I'm really enjoying Singapore, and I would like to stay longer, but as you just said, I have some other obligations in our institute and also have to teach, so I will return soon. So I will, during this next hour, spend some time telling you something about thermodynamics. And I will start with some very basic things, and I was, of course, told that there are many people of different backgrounds, but I hope that also the experts will at least learn something towards the second part of the talk, because then I will talk a little bit about how information and also how the concept of gambling, which is here mentioned on the title, plays a role in thermodynamics. But let me start with the basic things. So something that you certainly notice whenever you climb a hill is that you don't get anything for free. So if you want to gain altitude, you have to spend something. Maybe it's some sweat, but maybe you could also think of it like you consume some energy in some form. And we know that very well. We know that from any type of thing we want to achieve, whether we want to move with a car from A to B, or even if we think, we have to consume something in order to achieve the goal. So, and in the following few slides, I want to reflect a bit at what that means. So of course what it means in this case is just that there is a conservation of energy. So in other words, if we want to increase our potential energy coming from here to here, we have to take the energy from somewhere else. Maybe this is chemical energy that is then translated into this potential energy here. This law is of course very well known, at least not only by physicists, but it has been first formulated in that form as it's written here by Isaac Newton, who in particular looked at classical mechanics and realized that it's impossible to increase the energy of a closed system. So what are the implications of that? Over a long time, people have, of course, tried to move without effort, or to create something without effort, or maybe to climb a hill without effort. And they have come up with many very nice ideas of how this could be achieved. And this is one of the most well-known constructions. It has appeared many times in the history, and people have always, like maybe in different forms, and maybe it was not always obvious why it doesn't work, but the idea was always something like this wheel, which is also sometimes called the overbalanced wheel. So the idea is that you have here these little balls, and as you know, as actually every kid knows from sitting on a seesaw, if you are further outside, you execute a larger force. So you would expect that these little weights that are further outside will be able to lift these weights here, which are more close to the axis. But, okay, the idea is of course nice, but if you actually look at the whole picture and you also take into account everything, then you will find, not very surprisingly, that it doesn't work. So all this additional force will be compensated by some other movement you have to do, for example, to move this higher up and so on. So, of course, it's not a surprise to you that it doesn't work, but it's kind of conceivable that if you only know this law about forces, that the force or that the momentum executed on the axis depends on the force you execute, or the weight, times the distance, then you may first think that such a construction could work. And so many such things have been proposed, but they, of course, all are defeated by Newton's law. And this is what we know today. So you have to invest something, even if it's only electrical power, but it will not work forever. So this is what we can say about conservation of energy. But if you think about it, it's maybe also not a problem to conserve energy, because we also never destroy energy. So if you, for example, take a car and drive from A to B, or you fly from A to B, we don't destroy any energy because of the conservation of energy. The energy is always there. It's just transformed into a different form. So in some way, it's not really what we need to create new energy. So another way to think about it is the following. So this is just another instance where we kind of want to achieve something. Namely, we want to boil water. So we start with cold water and want to make it hot. So again, we have to pay a price. And the price we pay is that we have to invest some energy in a different form. It could be gas, but it could also electrical power. So we start with a full battery and end with an empty battery. But if you count the energy together, between here, the cold water, and the electric power, and here it's, of course, again the same. Nevertheless, it's somehow an asymmetric situation, because you know from experience probably that while we can easily go from here to here, I mean, that's what we do whenever we cook water, it's very hard to go from here to here. We cannot take hot water and somehow connect it to a battery and then hope that without changing anything else, at the end we will have cold water and a full battery. That doesn't work. But the question is why? The energy is conserved. And there's also a famous idea of how this could be used to actually do something useful. So you could think about, like, I mean, maybe I should briefly go back. So if you think about the direction from here to here, what happened here is that something that was warm got cold, but at the same time, some empty energy reservoir got filled, like a battery got filled. So if you now think of this as water that is reasonably warm, maybe the temperature outside here in Singapore, 30 degrees Celsius, and you transform it into ice water, then you may at the same time use this power, this energy increase, to drive a boat, for example. And that's this idea which is sketched here. So you kind of consume water, let's say at 30 degrees Celsius, then this engine cools it down. So cooling down means it takes energy out of the water and puts the energy into useful power to drive the boat. And that thing would be, in contrast to the previous things I mentioned, be called a perpetual motion machine of the second kind. So it doesn't violate the first, or it doesn't violate energy conservation, because the energy is the same before and after. The energy from the warm water was taken and put into motion here. And at the end, if you actually look at the water temperature, it will remain the same, because at the end, this energy that you put here into motion will again be transformed into friction, and will again melt this ice, and at the end you have a zero net energy cost. So this is a different type of perpetual motion, and one can again ask, why doesn't it not work? We somehow know it doesn't work, because if it did work, this would of course solve all our problems we have with energy. We could just at the same time produce ice cubes as we drive our cars. But it's impossible, as you also know pretty well, I guess. And this is the famous second law of thermodynamics, which comes in very different formulations. And one possible formulation is that that one just says it's impossible to convert heat into useful work by a cyclic process. So this cyclic process is important. You mean by that you have to restore everything else in the way it was before. So the second law now tells us that it's impossible to come from here to here, because it would just be in plain contradiction to the statement we had before. Namely, we would take this heat out and put it into something useful, into a charged battery, which we could again use to do some work. And also here, I mean, just to again stress what's wrong here. So it doesn't work because again it would, like this temperature of the sea, even if it's only 30 degrees, as long as it's warmer than what I produce, could be considered as heat, which would then be put into work. And the second law of thermodynamics tells us that this is not possible. So now this is, of course, a law, and we may now ask ourselves, is this law really true? I mean, should we believe in this law? This law has, of course, been discovered by observation of nature, but maybe people were just not clever enough, and there may be other things we could do in order to actually still break this law. And indeed, there have been many suggestions on how one could beat this second law of thermodynamics. So how could you transform heat into useful work? And one of the famous ideas is also known as Maxwell's demon. And I will explain it in different types, but let's say one basic version one could consider is the following. It would be the following mechanism. So you think of a gas cylinder. This gas cylinder is filled with gas, which is indicated, so the individual molecules of the gas are indicated by, or are drawn as these little spots here. And I've drawn here, this is an old picture, there are two types of spots, as you can see. There are the square ones and there are the circular ones. And you may, for example, imagine, that's one possible interpretation, that the square ones are hotter ones, they are the fast ones. And the circle ones are the slow ones. Of course, in a gas, you always have fast molecules and slow molecules. And now Maxwell had this idea of that there could be a very little mechanism, which he called a demon, or which is now called at least a demon. Maybe he didn't call it Maxwell's demon himself, but it's now known as Maxwell's demon, which is a mechanism that would observe there's a little hole here, and the mechanism would observe whether the particles that fly towards this hole are hot particles, fast particles, or slow particles. And then whenever there's a hot particle, a fast one, or in this picture, a square one, this demon would quickly open this little hole and let the particle pass, and then he would close it again. And whenever a slow circular one arrives, a cold one, he would keep this door closed. So now if you wait for a certain time, you will have this situation here. So you will have all the square ones here, the hot ones, and the cold ones here. And hot gas molecules means fast ones means they're hot. So at the end you have here warm particles, and here you have cold ones. Of course, in the whole process, if you assume that this door is very light and can be operated very easily, you wouldn't spend any energy. So to go from here to here, ideally, if you really carefully design this door, and I will come back to this problem, there's just no energy loss from here to here. So you haven't changed anything, you haven't changed the overall energy of this whole system. It's just that you have redistributed it. You have redistributed energy, which was all mixed here, into energy which is now in the form of some hot part, and energy, or only little energy, which comes in the form of some cold part. But now we have achieved something useful, because now we have actually cooled down a system and heated up a system. And maybe, I mean, for those who are familiar with thermodynamics or with heat engines, they know that this could then, if you have two parts of a system, a hot one and a cold one, this could be transformed into work. So there could be, you could now use that, for example, to charge a battery, and therefore violate the second law of thermodynamics. I will now, because I don't want to make this detour via warm particles and cold ones, show you a slightly different version of the same idea. But it's again, the idea is always that you have this little demon sitting here and doing something clever with the individual particles. And actually, I think this is really a question that is kind of interesting also beyond physics. I mean, I remember that when I was small and first realized or read about this Maxwell demon, I was always puzzled and wanted to understand, because I was always imagining that I could simulate this thing. I was imagining that to have a table that would kind of cause some movement of some balls, like you could just shake it a bit, and then I could implement this door and see what happens. And I couldn't imagine a reason why it wouldn't work. And indeed, if you do that macroscopically with balls and so on, it will actually work. But we'll later see that there's a problem if you go to smaller systems. So as I said, I would like to present a different version of this Maxwell demon, which is a little bit easier to understand. So if you didn't fully see the mechanism, how at the end I generate work, it's more obvious here. So the idea is the following. Here, you don't distinguish hot and cold particles. You just have a gas cylinder with particles, and you have a door that only lets particles pass in one direction. So it's kind of a trap door. The door can only open in this direction. Whenever a particle comes from here, it will remain closed. When a particle comes from here, it will open and let the particle pass. This is, again, a similar mechanism. It's even easier in the sense that you don't have to measure velocity. You just need to see whether the particles comes from here or here. Now, if you wait long enough, there will be more particles here, and most particles will end up here. And as you know, if there is now a gas which is entirely here, and here is vacuum, then there will be a pressure executed onto this wall. Now, what you can do is to connect this little wall with a weight in this way here, and we can furthermore assume that there is a mechanism that lets this wall is put into the system in such a way that it can move. So we can now release it, and then the wall will move to the left because of this pressure executed by these particles, thereby pulling up the weight. And if you have moved up a weight, that's the same as climbing a mountain, then we have done some useful work. So in other words, what have we achieved? We have started just with a gas, with a gas, and we have then at the end transformed some energy of the gas molecules into useful work. For those who want to maybe do this or think about it more carefully, you could even think about like that the gas molecules themselves don't provide the energy, but that the energy comes from a heat bath which holds the whole system at some constant temperature. And then while you let this door, while you wait for the particles to go into this compartment of the box, nothing happens with this heat bath. But now, as you let the gas expand, you know from thermodynamics that an expanding gas will cool down. So if you want to keep it at the same temperature, it has to take heat from this heat bath. So the net effect will be that heat from the heat bath will be moved into potential energy of this weight. And this clearly violates the second law of thermodynamics. So again, we can ask, why is this not possible? I would now go to another version, an even simpler version of this heat engine, which has been proposed by Leo Szilard in this paper here. It has a German title, but what this title says, it's about the reduction of entropy in a thermodynamical system by actions of an intelligent being. So this intelligent being is what he meant is this. It's something like this Maxwell demon. So some mechanism that does something intelligent. And probably the idea was that this thing here doesn't happen automatically. You will not in a natural system have such a door. And also you will not in a natural system have such a demon here. But of course we may think of some little intelligent being that does that. And the question is now, is this possible? And people have long arguments about whether this has anything to do with life. So if you have had a living being, then something is different. But let us now look what really happens. So Szilard's idea was to just look at the same scenario as before, but consider only one single gas molecule. So instead of now having these many gas molecules, we just have one. This makes it easier to think about it. But if you don't like to think of a gas with one molecule, you may still replace it by this many molecules gas I had before. But it's somehow easier to look at this process. Now we can go a little bit more precisely to the process. So what we want to do is to understand why is this process not possible? Or maybe the other answer could be maybe the second law is wrong. But if the second law was wrong, or if I found that the second law was wrong, I wouldn't probably be here now. So the second law is correct, and we want to understand why it is correct. So we have to understand why this little machine, this little door, cannot exist. What's wrong about this mechanism? But let's again look at the process in detail. And then we can think about each step and ask ourselves the question for each step whether a step is possible. And I now follow a description that has been proposed by Charlie Bennett. He's actually the speaker of the last public lecture that was given here. And so he has studied this scenario extensively, and he has also written important work about the resolution of this puzzle. So we start again with this little box with one gas molecule in it. And we assume that there are little pistons here that we can use later, and they are somehow connected to a weight as before. But I don't draw the weight because we now want to focus on the actual gas cylinder. So the first thing that is done is that there's some divider inserted. You just insert in the middle of this thing a wall which separates the two compartments so that the particle can no longer move from the right to the left or from the left to the right. Once you have done that, you may now have a look and see whether the particle is here or here. I mean, that's something which may be hard to do with pure eye, but you may do some measurement of whether the particle is found here or here. Now, if you found that the particle is on the right-hand side, what you can do is to move in this piston. This is also called the compression stroke. So you somehow now just reduce the volume of the whole thing. And the important observation here is that this doesn't cost you any work because the piston doesn't have to push against any force. There is vacuum here. There's no particle in this part. So you can move the piston up to the middle without executing any force. I mean, of course, maybe I should say to start moving the piston, you may apply a very small force or a little bit of energy that you invest, which you gain back when you deaccelerate the piston once it has reached the middle here. But at the end, the net energy consumption of this step is clearly zero. Now you can remove this dividing wall here. And now, as you remove this dividing wall, there will be a force executed on the piston, because now this particle bumps towards this piston, or if you think of a whole gas, it will execute the pressure on this piston. And now this piston can push something useful, like it can lift the weight as before. So we have now transformed the movement of this particle into useful work. And again, as before, you may want to think of it, this process as happening at the constant temperature. So if you want, you can think of a heat bath, which holds the particle at the same temperature, because the particle will, of course, lose a little bit of its kinetic energy while it moves this piston. And it may regain this kinetic energy from the heat bath. So now, this is Charlie Bennett, whom you have seen, and he has analyzed that. And an important observation he made is the following, namely that there was a measurement in the whole thing. I mean, maybe I should briefly go back. This was this step here. So at some point you measure whether the particle is on the left or on the right. You have to measure it, because if it was on the left, you would have had to push in this piston and do the whole thing on the, with the sides permuted. So you have to measure this particle. And people have for a long time argued that the whole machine doesn't work, because if I want to measure this particle, I have, for example, I need some quantum of light, because I have to have something that interacts with this particle. And the one choice could be a photon, some light particle, that I could then observe. And if nothing, as long as nothing interacts with this particle, I cannot observe it. So the measurement may require a certain amount of energy. So that was essentially the argument. And then people said, okay, of course, if this measurement requires energy, this could be even more energy than I gain in this whole process. And that would explain why this thing is not possible. But Charlie Bennett now argued that it's not true that this measurement costs energy. And he actually gave an explicit construction of how you could measure the position of such a particle. I don't want to explain the explicit construction, but maybe I can explain it in a kind of in a way which is more in a more abstract way. So in some way, observing a particle or doing a measurement is in some way just a copying process. Or maybe in the language for those, there are some people here from quantum information, it's actually not copying in the sense of cloning, but it's kind of copying in this sense that you have here something you want to observe, and you have some register in which you want to store your observation, and now you execute this logical operation. So from a logical point of view, a measurement is just this logical operation, which means what this means is that you look whether the system is in a certain state, and if it's 0, you don't do anything to a memory register. If it's in state 1, you change the memory register. Now, if you start with a memory register in position 0, you will now, in the memory, looking at the memory register, know whether the particle was on the left or on the right. So what Charlie Bennett, the argument of Charlie Bennett was that this measurement, this copying operation, is a reversible operation. And the reversible operation can always, in principle, be done without any energy cost. If you don't believe that, then you can actually have a look at Charlie Bennett's papers, and he has really a mechanism, a classical mechanical mechanism that does this measurement. So in principle, there is such a measurement. It's just very hard to do it in practice, but there is no fundamental reason why we cannot observe the particle, where observation really means just that depending on the position of the particle, there will be some entry in a memory register, which we remember, which will tell us whether the particle was seen on the left and on the right, or on the right. So this was not the problem. So let's go back now and see what's wrong. So we still have this second law, and we have this Hiller engine. So obviously the measurement is not the problem. So what else is the problem? Let's go through these steps again. Let me now also draw this little memory register that holds the output of this measurement that I do. So there's, of course, this first step where we insert the divider. So inserting a divider can, again, as before, as I explained, that this piston can be pushed to the right without any energy, can in principle be done without any net energy cost. Because you charge a little energy to start moving it, and then you get this little energy back once it's inserted. So this is unproblematic. Then there is the measurement, of which we just have seen that it doesn't cost us any energy. Then this I already mentioned. So here, this was the main idea, of course, behind Hiller's engine, that this step doesn't cost any energy because there's no pressure here. Then we remove the divider, and for the same reason as before, it doesn't push against any force, so there is no energy cost in this step. And now, the last step is, of course, the step that actually generates work or transforms work from the heat bath, or energy from the heat bath to useful work, which is this expansion step. And this also works. I mean, that's what we can always do. By the way, this is exactly what happened, what you could do. I mean, if you want to verify that this step works, you could take a tire of a bicycle and let the air expand from that. And then you will see, you could, of course, in principle, think of having a little wheel in the stream of air that now comes from from the tire. And that would kind of be some work that you could execute, but at the same time, the tire will actually cool down. This is really transformation of heat into work that you could do once. But of course, once the tire is empty, you have to pump it up again, and that would, so it's therefore not a cyclic process, and would therefore not violate the second law of thermodynamics. But this is just to say that in one step, in a non-cyclic step, it's always possible, as it's done here, to actually transform heat into work. So, but there is one step we forgot, and this will resolve our thing, actually. We haven't yet a cyclic process. We still have this memory register. So you remember, I always drew this memory register here. And the memory told us the particle was on the right. Now when we started, remember, it was important that when we started, the memory register was in position 0. This is actually really important, because if you think back of this scheme here that I have about how a measurement is implemented, the measurement is only a reversible operation if you start with a memory register that is in a well-initialized state. So it's important here that at the beginning, this register is in some well-defined state, which I called 0. So we have to make sure that at the end of the process, we reinitialize it again. So we should be exactly in the same situation as when we started. And then we can start the whole process again. But it's important that we do that step. So now the question is, does this step cost us any energy? And you may think, okay, that's just a logical step. We just forget the information that we have in the memory register and write the 0 in our memory register. I mean, you could even think of you being this daemon, and you would just erase it and then write the 0. So why should that cost any energy? Of course, if you write, it seems to cost any energy, so maybe that's the reason. And that's indeed the case. And that's what is known as Landauer's erasure principle. So in some way, it's this very last step of which you didn't even think before, like this erasure of memory, that actually costs energy. And this was a discovery, or at least an idea, that Landauer proposed. He was a physicist who, you see, we are coming closer and closer to current time, because we started with Newton and then went on to Kelvin, who actually lived also in the 20th century. He died in the 20th century, and now we are already in the almost in the 21st century. So this was another important contribution. He realized that we cannot, it's impossible to erase a bit of information like this little register without any energy cost. And actually, what he proposed is that the energy cost, or the work cost we need to erase the bit in this step, so the amount of like the amount of, let's say if you think of it like that, the amount of electricity you would have to take from the battery to reinitialize that register has to be as large as the work you gain from this whole process. Of course, if it is as large as the work you gain, then there is no net energy left, so the whole Ziller engine will not be useful for you. You will use everything you gain just for this erasure of the bit. Of course, you have to remember that you don't, of course, gain much work, because there is a single particle here. And if you just have a single particle, there's, of course, a very small force executed on that piston. So you have only very little energy, but this energy will just be used up by this erasure. That's what Landauer proposed. Now, let's see what that now means. So we have now, in some way, if we believe in this Landauer principle, that's, of course, now a new thing that comes in. But as long as we believe in this principle, we have resolved our paradox, because now we have identified one step, this step 6, which requires work, and so there's no paradox left. The whole Ziller engine doesn't work because we've just forgot that step. So in some way, if I summarize this argument of that Bennett and Landauer made, I mean, this is now kind of put together by Bennett. So Bennett combined all these things together to make the following argument. And if you for a moment go back to a big engine, of course you can do everything with many particles. Then you can now ask again, what's going wrong? Why does this engine that I described before not work? So again, the door works. But the important thing is that this door we shouldn't forget that this door has to have a memory. This door cannot just let particles pass from here to here without first measuring whether the particle was here or here. So whether this is really knowledge or not is not relevant. The important thing is that the operation of the door really depends on whether the particles comes from the left or on the right. So somewhere in this door, at some point, the information whether the particle was on the left or on the right is present. So you could think of this door as having some internal memory, where whenever a particle came from the left, it has a value 0, and whenever a particle comes from the right, it has a value 1. And importantly, if you say, okay, I want to implement such a door without such a memory, then you will not be able to do that, because then it will no longer be a reversible machine. So Bennett's argument for saying that there is this door, and this measurement can be done without any energy cost, was conditional on the assumption that you have access to such a memory where you store the outcome of your measurement. Now, okay, what you have is, what this means is that you could in principle really construct such a trapdoor. You just need to provide it with some memory where it can write down this string here. So in other words, if you connect your Maxwell daemon to a modern iPhone or so with a lot of memory space, you can let it operate for quite some while. But at some point, the memory space of the iPhone will be used up, and then it can no longer write its information somewhere, so you have to erase the memory. And it's this memory erasure that will now cost work. So what I now said is somehow something that really establishes a connection, as you have already seen, between information and energy. Because actually, if you think about it, the reason why Maxwell's daemon didn't work was that I said that you have to erase information, but information is somehow a very abstract term. How can it be that information has something to do really with physics? How can information be the reason that a daemon or that something doesn't work, that a thermal engine doesn't work? And in order to explain that, I will want to very briefly tell you what information is, because I was now just using this term and said that there is this information erasure problem, and that Landauer said that the erasure of information costs energy. So what is information? There are different ways of describing what information is, and I will very briefly show you both approaches, because they give you probably then together an insight of how information theorists think about information. And maybe the best way to approach this question is to just ask, how could we quantify information? So you somehow may have an intuitive notion of information. For example, if you watch the news on TV, you probably think that you now gain some information. But maybe we can try to quantify that. Maybe you can ask yourself, how much information do you gain when you watch the news? And one idea is to Kolmogorov, and he had the following idea. So he could, for example, ask, what is the information content of that picture? How much information is there? This picture has many little features, so you may think that actually it's there's a lot of information content. Now, Kolmogorov's idea was to say that let's look whether there is a more clever representation of this picture. And this picture, those who have seen it before, is of course can be created with a very simple program. So if you want to generate this picture, you just have to write down this program here on a computer and run it, and you will get this picture with even more features than can be shown with this resolution. So in other words, all the information that is in the picture is already in these few lines here that are written up here. And that was Kolmogorov's idea. So Kolmogorov said that we quantify information by the amount or by the size of the shortest description we need in order to reconstruct the whole thing. So in other words, Kolmogorov's answer to the question, how much information is in this picture, would be that the information in this picture is lower than the size of this program. So he could count the number of symbols of this program, and then this would be an upper bound on the information. If we're not sure whether this is the shortest program. If he knew that this is the shortest program that creates the picture, then exactly the length of this program would be the information content. So you can now apply this thing to, for example, the news. And it somehow makes sense. So if you, for example, could summarize the content of the whole news that you saw on the TV in just one sentence, and you could somehow from that reconstruct the whole news, then obviously there wouldn't be much information content in the news, because everything is in this sentence, even though the news maybe lasted for 1 hour. Because what is relevant according to Kolmogorov is just a short description. But on the other hand, if you see something which is really complicated, then there may be more, there may be not such a short description. Let me now briefly go to the other notion of how to quantify information. And this is closer to what we are actually going to need for the last part of my talk. This is Shannon's idea. Claude Shannon, I mean, we had here these 2 pictures of the guy. So Claude Shannon was essentially the founder of the modern theory of information. He's a very influential person in that sense. And he had this idea which is somehow not based on the size of programs. It's rather based on something that one could call chance. So maybe people from Singapore recognize that. That's that's called the 4D. I think you have to somehow guess 4 digits of a number, which are then randomly chosen. So Shannon's idea was the following. He said that the information content of a message, or let's say of the news, depends on how surprising the message is. So for example, if you watch the news and you're never surprised at all, you could always somehow predict what is there, then Shannon would say there is no information in this news. However, if you turn on the news and you see something that surprises you, then Shannon would say this has now a lot of information content. So you can make that even more quantitative. You could actually think now of this little game, of this lottery, and ask yourself, if you have 4 digits that you want to guess, and now, let's say you played in this lottery, and I would now tell you just one thing. I would tell you, you won. Now, how much information is in this answer that you won? That I'm just telling you essentially 1 bit of information. I'm telling you, you won the lottery. There's, of course, a lot of information, because you will be surprised that you won. Presumably, you wouldn't expect to win in the lottery. So, therefore, according to Shannon, there would be a lot of information. If I told you you didn't win, that's probably what you expect, because you usually don't win, then there is almost no information content in this message. And it also makes sense, because in case I told you you won, you immediately know what the numbers are, because they are the numbers that you actually chose. So these are 2 notions to quantifying information. So how can we use them now? So let me, in order to maybe somehow make a connection between them, also mention that Shannon's notion of information can also be seen as how many yes-no questions do I need to answer on average so that you can reconstruct the message. So in some way, Shannon's notion is still very close to Kolmogorov's notion, because you could still see it as kind of the size or the number of bits you need in order to specify the message that you have seen. So in other words, while Kolmogorov is talking about the size of a program, Shannon would just say, how many questions do you have to answer? And he found out that if you ask questions which always have, like for example, if I have to guess a number, I could always kind of ask whether it's larger than that or smaller than that. And the number of yes-no questions I have to ask is optimal if each time I ask a question, I have a 50% chance of answering yes or no. And then one can show that this is very similar to Kolmogorov's notion. So let me now go back to Landauer's principle. And so now you have maybe some idea of what it means that we erase information, because information is really now the like some information can be quantified either in the way of by Kolmogorov or by Shannon. So in order to give you some numbers, I said information erasure costs something, so we can actually give explicit numbers. So it turns out that if you do the erasure at room temperature, then in order to erase 1 bit, you need a very little energy. It's 10 to the minus 21 joule. So that's, maybe this number doesn't tell you much. So let's look at something bigger. So let's assume that you erase the content of an iPhone. I assume that it has kind of 64 gigabytes. I'm not sure whether this is accurate, but let's assume it has that amount of storage space. Then you would need 10 to the minus 9 joule. So what does that mean? That means that if you would erase the iPhone, let's say, 1 billion times, the amount of energy you need is 1 joule, which would correspond to essentially lifting, let's say, one Swiss chocolate 1 meter above the ground. So that's essentially the energy you need to erase your iPad 1 billion times. So it's not much. But still, it's noticeable, so it's not nothing. So what does this now have to do with our quantification of information, as I explained before, that was introduced by Shannon and Kolmogorov? So we could now ask, like, if we have something like this picture and we want to erase that picture, how much energy does that cost? And so the idea is somehow that you can now apply, for example, Kolmogorov's idea, but the same thing would work with Shannon's idea, and compress the picture into this small program. And because you can reconstruct the picture from the program, the operation is reversible. And what is known in physics is that all reversible operations can be done, again, without energy. So you can, instead of erasing the picture, you first transform it into this program, and then erase the program. But the program is now pretty short, so you need only a certain small amount of battery power to erase that program, and therefore to erase the picture. So you see, there is now a very direct link between the amount, like the quantification of information that has been introduced in information theory, which was in terms of somehow minimum sizes of programs, and amount of work we need to erase something. So there's even a one-to-one relation. So the information content of a message is really the relevant quantity that tells us how much work we would need to erase the message. But what does this now have to do with gambling? So I'm now coming towards the end of this lecture. So you saw that we had this step in the CLR engine. And what we did in this step is to somehow measure the thing, and for that we needed the memory. Now, what we could do is to say, this was kind of still the problematic step, because if we didn't have to do the measurement, we will also never have to erase the memory, and therefore we would not be subject to the restrictions that come from Landauer's principle. So what if we don't measure? We could just guess that the particle is either on the right or on the left. Of course, we can do that. Maybe we are right. And if we are, so first of all, notice that it's important that we guess correctly, because if we guess wrongly, so if you would, for example, have guessed that the particle is on the left rather than on the right, then we would push in this cylinder here. So we would then push the cylinder against some force. So our weight that we have connected to this cylinder would actually be lowered, and we would not gain energy from the process. We would actually rather lose energy, because we would have to execute a larger force to push in this cylinder against this particle, because there's a small volume here. So we'd actually lose the same amount of work that we would gain if we guessed correctly. So, however, if we guess correctly, then the process works. So if you're just lucky, then we can do our work extraction. So in some way, it's really like gambling in a casino, because if you are correct, you gain something. You don't gain money, but you gain work. And you don't pay a price. So in some way, you could also say that this CLR engine works in the same way as you can win in a casino, because if you're lucky, it works. And if you're unlucky, you lose something. So the idea that you could now pursue is to say, let's just have this gambler here, and he just randomly chooses, or he randomly guesses where the particles are, and then at the end, if he's lucky, he can maybe lift his weight and gain a lot of work. However, and this is pretty obvious, that each time you do such a guess, you're of course wrong with probability 1/2. So with probability, and this will soon, so it will soon happen that you're at least for one of the guesses wrong. So in other words, you cannot really apply this method for a large system. However, if you have really some small system like the one I drew here, with only few particles, the chance that you are lucky is still reasonably large. probably larger than in a lottery. So if you would actually have this little engine here, you could probably extract work with a success probability that is larger than if you play this 4D game that I mentioned before. So what do we learn from that? So again, you remember now the notion of surprisal that Shannon introduced. And it's actually interesting to see that it's exactly this surprisal that is here important for this consideration. Because it's, so Shannon actually introduced really a quantity that he called surprisal. And this quantity is essentially directly the probability by which you are successful. More precisely, it's a logarithm of that because he wanted to treat it as an entropy, but it's essentially directly given by the probability that you correctly guess in your game. Now, if you combine that with this idea here, then you see that the surprisal, or like the information content according to Shannon, is really directly linked to the probability that you will be able to extract work in this system if you randomly guess, if you do it in this way with this gambler here. So Shannon's notion of information can not only be used to kind of think about scenarios where we extract work for certain, but it can really be applied to scenarios where we want to probabilistically extract work. And it will tell us exactly what the probability is to be successful. It's exactly the entropy. It's 2 to the minus the entropy for those who know how this entropy is exactly defined. Okay, so what have we learned from all that? So what I just told you now is that Shannon's idea of a surprisal, what I mean by that is his idea of measuring information in terms of the probability by which something occurs, establishes a connection between gambling, between chances, and between information. On the other hand, what we know from Landauer, this is what I told you in the first part of the lecture, is that there is a very close connection between information and work. If we have information about something, so if we have this measured information, then we can use it to extract work. That's the idea of Szilard's engine. It's just that in order to gain the information, we have to measure, and in order to measure, we have to have an initialized memory register, and that costs, again, work. So there is this very close connection between work and information. And this brings me to the conclusion. We have now seen 2 connections, and this, of course, suggests this is, of course, transitive. So what we can now see is that if we connect Shannon's idea that information and chance are connected with the idea that information and work are connected, we get also a relationship between chance and work. So we can say that probabilities of being successful, of guessing correctly where particles are kind of connected to work. And this can be made really quantitative using the ideas of information theory, which are here in the middle. Okay, so this is all I have to tell you. Thanks a lot for your attention. Sure, yes. Yes, if there are any.
You never mentioned the word entropy. I mean, was it on purpose, or?
Yes.
I didn't notice that you mentioned.
No, it's I didn't mention it for the simple reason that I was asked to speak in front of a general audience where even school classes could be here, and I was expecting that they don't know the term entropy. So that was the only reason. Otherwise, I would have formulated many of these things as entropy. So in particular, maybe just to be a little bit more extended. So I would have, for example, said that here, if you measure information in the terms of as Shannon did, then the surprise, like I said, that what is relevant is the probability or how surprised we are. And how surprised we are can be quantified as the probability that we would have guessed what it is. And this would be actually used as a definition of entropy, just take the log of that. And now, it then turns out that the length of this program is again exactly the entropy. And so now if we want to make everything, so I just said we can make everything quantitative. So now what it would mean here is that the entropy of that information here would be proportional to the amount of battery power we need to erase the thing. Now if you go further to that, then it's of course again, like here, so the success probability of this demon is 2 to the minus the entropy of the gas. And now if you go to the final picture, we see that the entropy is really allows us to make that quantitative. So of course, the connection between here and the entropy is this Landauer principle, which would tell us that the amount of work is the Boltzmann constant times the entropy times the temperature at which we execute the process. And the connection between here and here would be that the chance is 2 to the minus the entropy of that. So there was nothing against entropy. In contrary, I work on entropy, but I try to somehow keep it on a general level. Yes. Yes. In some way, yes. What this will give, I mean, this is in a particular instance of that. But in some way, it's more general because as I tried to explain with maybe this slide here with the compression, like there is something non-trivial happening when we go like from information to erasure. So what this implies is that it's really, like you could first think it's just a number of possible things that could happen that is relevant. But the entropy of something could be much smaller than the degrees of freedom. So if you now, I mean, this is maybe now a little bit more technical in the talk, but somehow the entropy is in general a quantity that can be arbitrarily much smaller than the degrees of freedom. In particular, the entropy, of course, according to Shannon, could even be 0 if I know everything about the system. Now this means that the chances I have are not just this chance that this will just happen, it's more the chance that I guess I predict something correctly given some information I have about the system. And this chance can be in principle much larger than the chance that this body will just jump up. Because I could, for example, have additional information about the system so that the entropy, the information theoretic entropy about the system is much smaller than, let's say, the number of degrees of freedom of the system. And then, of course, it will not jump up, but something predictable will happen which I could use to extract work from the system. Of course, that's a special case. So this, what you mentioned, is kind of the special case if I have no information at all about the system and all degrees of freedom, if I have kind of an equilibrium state. And yes, so I would say, I mean, the example is, of course, somehow something like a small engine. Okay, I mean, if people are now, I mean, okay, I didn't mention this, but this is a small engine. But if you now look what people in the labs are doing, for example, in quantum information or in quantum sciences, they have systems of that size. Like they have ion traps with maybe 16 ions and so on. And you could kind of think of using such systems to kind of, like you're there in this intermediate regime. You have really systems where this picture is really appropriate. You have exactly maybe this number of particles. And here the chances that you are correct are of course larger. You may in particular know even more about the state than just that it's uniform. So there are And so, yes, so this is kind of a practical example. So if you, I mean, we have actually, I mean, we can maybe talk about that later. So there is, for example, in Switzerland, we have some collaboration with a group that does Eintraps, where we look at such things and see whether one can really like observe that directly. But so the example are small systems, so that the probability, so that the information is close to zero. So because the gambling, so the probability of being correct is 2 to the minus the entropy. So you have to have a system where the entropy, where the reference is kind of a pure state, that would be entropy 0, where the entropy is very small, because otherwise this probability will, because it's exponential, will be very small. So any system where you have sufficient knowledge so that the entropy is reasonably small is an example. Yes, that's absolutely correct. Yes. Yes, but you are kind of in the, I mean, the interesting thing, of course, I mean, I never said, hopefully, that the second law is wrong or so. So what we can do is now to just analyze a mesoscopic regime where the notion of a second law doesn't apply in the normal sense. But we're also not in the so if you talk about one particle, then you may also say, now it doesn't make sense to apply thermodynamics because we can just describe everything. So here we are kind of in an intermediate regime. I'm not claiming that the amount of work you gain here will be really useful for, let's say, macroscopic purposes, but we are in a regime that is somehow in between what we did so far with thermodynamics and what we are, enter a regime which is so small that thermodynamics doesn't make sense at all. And in this regime, there is some work. So it will more point to the question of what does it actually mean. So of course, because the work is so small, you may indeed ask this question, is this still work? And in some way, the answer would be, it's work with that probability. Do you that still call work? So it also points towards some interesting questions. But yes. You have to ask.
So, in your picture of the fractal set, of course, a lot depends on whether you actually have the idea how to generate.
Yes.
Is that your framework?
Yeah, that's a very good question. So actually, there is of course. Yes. This is okay. So thanks for asking this question. So of course, in general, if I now see such a pattern, I have of course no idea how to generate it with a short program. And so what does that mean? So at the end, my ability to actually extract work from a system will depend on the knowledge of this compressed thing. So if I don't have it, I cannot do it. So, and this is actually why this idea of Kolmogorov, in contrast to the idea of Shannon, is more problematic. Because for Shannon, I don't need to do that and never need to guess anything. For Kolmogorov, I really need to find this shortest program. So if we now would quantify information in terms of Kolmogorov, which I didn't at the end, at the end I was mostly talking about Shannon. But if we did it with Kolmogorov, the statement would be the following. The statement would be, in principle, if you have such a thing, there exists a machine that extracts work. I simply don't know how to construct it. So it's still a statement about the existence of a machine. But in addition, the statement would of course be that if once I find the program, I can actually construct the machine in principle. Now, the reason why I'm happy that you asked this question is that this also illustrates why actually a big difference between these two. So I somehow may have suggested that they are very similar, and they are similar in the sense that at the end the size of the thing is somehow like corresponding to the smallest compression. But in the case of Shannon entropy, the whole notion is defined on a different concept. It's namely, here I'm talking about one particular picture. Whereas in Shannon's case, I talk about a probability distribution over different things that can potentially happen. But again, in this case, instead what I would need to know is the probability distribution. And if I don't know that one, it may also not work. So the price I pay here to go to Shannon is to know the probability distribution, but usually I can infer that by experiments. Whereas the other thing, this program is just hard to find. It's not even computable. So there's not even an algorithm that gives me the program. Okay, there's still a question. There was one there. Yes.
I can ask you a follow-up to this question then. But then now you get problems with describing this thing with Shannon, is that if you want to resolve this at the infinite resolution, out of all the infinite resolution pictures you could have, it would take an infinite amount of Shannon entropy somehow, whereas within a finite amount of...
Yes. Yeah, that's a good question, but the answer is similar. I should maybe again stress that the notion of Shannon is based on how surprising a message is. And this depends on the probability distribution. So mathematically, it's a completely different object. So the Shannon entropy is a function of a probability distribution, and the Kolmogorov complexity, or Kolmogorov entropy, if you want, is a function of the actual object, of the actual picture. So in order to apply Shannon to that picture, I would actually need to have a process, oh, now the picture has gone, but which produces pictures at random and then determine the probabilities by which the pictures arise. If I don't have this process, I can actually not define Shannon entropy. So Shannon entropy, I still have to pay a price in order to be able to talk about Shannon entropy. I need to have a process which is well defined and for which I know the statistics, essentially.
Well, so I was thinking I spent the last hour where things got very difficult now. Explain them in ways that the audience will appreciate. I was reading Professor Renner's CV and noticed that he actually was a teacher before. And now I understand why. Excellent scientists also have the same idea as well. So before we end this session, on behalf of the Institute for Mathematics, I'd like to present to Professor Renner a small token of
Oh, it's inside. Oh, it's okay. Thank you very much.
Please join me.
Okay, thank you. So it's a Silo engine. Okay. Thank you very much.